Welcome to video 8.4. We're going to look at a couple different properties involving integrals today. When we had initially defined our definite integral, we assumed that a was less than b. However, we can still see what it would give us if a is actually greater than b. So when we had a was less than b, we did b minus a over n to do our width of our rectangles. Because b was bigger than a, when we subtracted b minus a, it gave us a positive number. Well, now, if it's the other way around, a minus b there, it should give us a negative number. So essentially, we're saying the smaller one is coming first, and the larger one is coming second. So if you have, say we had the integral from 1 to 3 of f of x dx. Let's say we knew that that was equal to 7. Well, if we did the integral from 3 to 1 of f of x dx, notice here, when you switch the a and the b, to switch the spots, it just negates what your area under the curve was. So now we would have this be a negative 7. Now, if a and b happen to be the same, we'll just end up getting 0. Because if you think of it back to our rectangles, that's telling us that both endpoints are exactly in the same spot. Well, so then there's no space under the curve, so the area under the curve is just 0. Here's some properties of integrals. You can pause it here and copy all 4 down, or we're going to look at each of the 4 individually on the next few slides. The first one we have is if you're taking the definite integral of a constant. So remember, what we're really doing is the area under a curve, and by that we mean the area between our curve and the x-axis. So if we just have some constant, that means we have a horizontal line. So the area under your curve will just be a rectangle. Well, the height of that rectangle is whatever the constant is, and the base of that rectangle is whatever the difference is from b minus a. So like, for example, if a was 1 and b was 7, you can probably just think about that and know that this must be 6. Well, where that's coming from is doing 7 minus 1. So in general, this side will always be b minus a. So therefore, our area of that space, because it's a rectangle, is just length times width, or base times height, however you want to think of it as. So therefore, our area is just the constant times b minus a. So a specific example, if we had the integral from 2 to 8, we'll say, of 4 dx, well, that's just going to be our constant 4 times the difference of 8 minus 2. So it would be 4 times 6. So 24 would be the area under our curve. And that's like saying an area of a rectangle, essentially, because our curve is actually just a horizontal line. The second one we have is if we're doing the definite integral of 2 separate functions being added. Very similar to when we do summations, when we did limits. We can do those integrals separately. And here's a visual of what that's showing here. So the black line, you have the graph of x. The blue line, you have the graph of g individually. Well, if you put those together, that's just f plus g, that reddish, pinkish one. So you could do their areas separately and add them together, and it would be the same as the area of the total. The next one is if you have a constant. And again, we've seen this with limits, with summations. If you have a constant, you can just pull it out front, because the constant doesn't have any x with it. And you can only do it if it is a constant. So for example, if you had the integral from 1 to 4 of, say, 7x squared dx, that would be the same as 7 times the integral from 1 to 4 of x squared dx. Okay, so that's just saying that you could bring the constant out front. And our fourth property is subtraction. Well, if you're doing subtraction, just thinking of it as adding a negative, we already know addition we can split up, and think of the negative as being something you can pull out because it's a constant. So that basically proves why property 4 is true. And we've seen with summations and with limits that if you're subtracting two different things inside, that you could do it separately. So pretty much the same idea here with our definite integrals. So we're going to use those properties to evaluate this definite integral. And we're going to use the fact that the integral from 0 to 1 of x squared is just 1/3. Okay, we'll see how to actually calculate that eventually, but for right now, we'll just tell you that it's 1/3. So we've got addition, so let's split this into two separate parts. Okay, so that's using our property about addition. And then we can use our, in that second integral, the property that you can pull the constant out front. So this is really the integral from 0 to 1 of 4 dx plus 3 times the integral from 0 to 1 of x squared dx. And now we can go about evaluating this. So the first integral there is just like the constant example we did before. So we'll have 4 times b minus a, so 4 times 1 minus 0, plus 3 times, we had set up here that the integral of x squared from 0 to 1 is just 1/3. So this will just be 1/3. And we can now evaluate what this will give us. This is just 4 times 1 plus 3 times a third is 1. So it's 4 plus 1, which is just 5. Another way we can use these properties is, say you have a big section of graph. Well, you can split it into like a left section and a right section, find their areas under the curve for those sections, and then add them together. That's essentially what this is saying. So if we had the integral from, say, 1 to 4 of f of x, plus the integral from 4 to 6 of f of x, that should be the same as if we took the integral from 1 to 6 directly of f of x. So basically, you're splitting it into a left-hand portion of from x is 1 to 4, and then from 4 to 6, and then you're just adding them together to get the whole thing. And it makes a lot of sense when you see the visual on this next slide. So that purple part there, you have the first part from A to C, and then the other part from C to B, or you could think of it as just the whole thing all together from A to B. So you could do them separately, or you could do it all together, and they would equal the same thing. So let's say they told us from 0 to 10, the area is 17. From 0 to 8, we know it's 12. Well, what would it be from 8 to 10 for f of x? Let's imagine we had just some like random curve. We said this was 10. We said this was 8. Well, they told us that from 0 to 8, this part of it is 12. And they told us the whole thing. So I'm just going to show that with a bracket, kind of. So that whole area is going to end up giving us 17. And we want to know, what is it just from 8 to 10? So essentially, you can think of it as 12 plus x has to equal 17. So therefore, x, the area we're looking for, is just 5. Now, they could have given us different stuff and asked this slightly differently, they could have given us the two small parts and had us find the large part as well. Now, each of these 5 things we looked at, it doesn't matter if A and B are equal or if one is bigger than the other. 3 other properties that it does matter which is larger. These ones only work if A is less than or equal to B. Our first one is saying if our function is positive on our interval from A to B. So basically it's above the x-axis, then our integral has to be greater than or equal to 0. Well, that makes a lot of sense. If your graph is always above the x-axis, we know when you're above the x-axis, that area is positive. So if the graph is always above the x-axis, there's no way it can't possibly be positive. It would need to go below the x-axis to be negative. Number 7 is saying if the graph of f of x is always a higher y value than the graph of g of x, then the integral of f of x is bigger than the integral of g of x. So that's saying the area under f of x should be larger than the area under g of x. Well, if the graph of f of x is always going to be higher, then that makes sense. The area between that graph and the x-axis should be larger. And the last one is saying if you have 2 constant values that your function stays between, that the area of the 2 constant functions should be the upper and lower bounds of the area of our actual function. And that one might be a little confusing to understand, but it's a bit easier with a picture, which I'll show you on the next slide. So think of capital M as this horizontal line here. So it's saying the area of that big rectangle is our upper bound. The area of this rectangle is our lower bound. And the area of our function f of x must be something in between those 2 areas. Okay, so notice the y values of f of x are staying in between those 2 constants. So therefore, the area of the rectangle for the small one should be less than the area under f of x, and the area underneath the larger one, capital M, should be bigger than the area of f of x. And just a proof of where that's coming from, if you take the integral of all 3 parts, well, we know when we have a constant, you just do that constant times b minus a. So that's where the lowercase m times b minus a is coming from, and the uppercase m times b minus a is coming from. And then in the middle, that's just a notation that represents our area under f of x. And we're going to use that to estimate this integral here. Okay, the function of e to the negative x squared looks something like this. Well, we are looking at it from 0 to 1. So here's 0. Let's say 1 is somewhere here. In that interval, because it's a decreasing function in the interval, the absolute maximum must be when x is 0. So when we set up our inequality like we saw back on this slide, we're going to have this be when x is 0, and we'll have this be when x is 1. Because when x is 1, that's when our smallest value on the interval is, and when x is 0, that's when the largest value is. So we're going to have e to the minus 1 squared, because that should be the largest. Oh, sorry, e to the minus 0 squared, not 1. And it should be the smallest when it's at 1, so we'll have e to the minus 1 squared. And then in between is our function, e to the minus x squared. Well, this is going to give us e to the negative 1. And this will give us to the 0. Anything to the 0 is just 1. Well, now we're going to take our integral of each from 0 to 1. Well, on the left and the right, we have constants. So when we do the definite integral of a constant, because e to a number is just a number, it's a constant, we'll do our constant times b minus a. That needs to stay less than or equal to the integral from 0 to 1 of e to the minus x squared dx, which that's what we're trying to approximate. And this will be 1 times our b minus a, 1 minus 0. And again, the middle is what we're trying to approximate there. Well, 1 minus 0 is 1, so this is just e to the negative 1. Now, e to the negative 1, put in a calculator, is roughly 0.3679 or so. And over on the right, we have 1. So this is now our estimate for what our area under the curve of our function is from 0 to 1. We just showed that that area must be in between 0.3679 and 1. And we'll show you a visual of that on the next slide. Here's the y value of 1 over e. So this area here, that was our 0.3679. Here, this was our e to the 0, really. Oops. So the red area, that's our area of 1. It's 1 by 1. And then we said that our function's area must be somewhere in between there. And you can pretty clearly see the area under e to the minus x squared is definitely in between the areas of those two rectangles. That's it for this video. We'll see you next class, period.